Now we can talk about scatter plots. When each item in the population can be classified simultaneously by two different numerical variables, this is a very easy situation to represent graphically. Suppose for a set of houses in a particular neighborhood, we measured both the price of the house and the area in square feet of the house. Two numerical measurements for each house. Then what we could do, we could make a graph like this, and it'd be very easy to see the relationship. So here, every dot is a particular house. The horizontal position of the dot indicates its area in square feet. The vertical position of the dot indicates its price. And so if we know the price of the house, we know the area in square feet, we can place that house on this graph. Notice interestingly that the price starts at 0 and goes 0, 1/2, 1, 1.5, 2. It starts at 0, but the area doesn't start at 0. The area actually starts at 500. It goes 500, 1,000, so it has equal intervals. It just doesn't start at 0. So as we might expect, as area goes up, price tends to go up. This pattern is known as a positive correlation. When one variable increases, the other tends to increase. And by this increase, we mean that if we look at the sweep of the whole population, there's this kind of upward trend of the whole mass of data points. That's what constitutes a positive correlation. On average, as area increases, then the price also increases. It's kind of an average statement or a probabilistic statement. It's very important to notice a correlation is about an overall pattern in the data set as a whole. Correlation in the whole data set does not mean that the pattern will be obeyed between every possible pair of points in the set. In fact, it's very easy to find pairs of individuals that don't obey the general pattern. So the general pattern is area increases, so price increases. But suppose I look at that house and that house. Well, as area increases, the price decreases. Or if I look at that house and that house. Or if I look at this house and this house. So it's very easy to find individual pairs that don't obey the pattern. That's not what a correlation is about. A correlation is not about nitpicking and looking for individual pairs and the relationship between these pairs. It's about a general pattern in the population as a whole. That's what a correlation is. In general, the two variables will be represented on the two axes. Any variable may or may not start from a 0 value. As we saw here, one of the variables did not start from 0. Each individual or item will be represented as a single dot, and its position will be determined by the value of each variable. So here, every house was a single dot, and its variable was determined by the price and by its area in square feet. Questions may ask about regions of the graph. That is, how many points are above or below such and such a value of one variable or the other variable. So for example, how many houses cost more than $2 million? So we'd be looking at $2 million and looking at the houses that lie above this line, and these points here in purple, these are the ones that are either at 2 million or a little bit more. And so there are 6 houses on this graph that cost more than $2 million. Alternately, we could ask how many houses have an area less than 1,500 square feet. Well, here we would draw this vertical line, and we'd be looking to the left of this vertical line, and of course it would be these houses here. So that's 7 houses that have an area less than 1,500 square feet. Here's a practice question. Pause the video and then we'll talk about this. Okay, how many houses have an area of more than 2,000 square feet but costs less than $2 million? So here's 2,000 square feet. They have to be over here. And here is $2 million. So we're going to say that this point here is either at or a little above 2 million. So we're not going to count that. And it's only 1, 2, 3, 4. Those are the points that fit this criteria there are 4 houses that have an area of more than 2 million square feet but cost less than $2 million. Some of the questions just involve counting the number of dots in certain rectangles of the graph. The test also asks about correlation. A positive correlation, as we said, is a pattern in which as one variable increases, on average the other also increases. A negative correlation is a pattern in which as one variable increases, on average the other decreases. So here are some positive correlations. All 3 of these demonstrate a positive correlation. The correlation strength varies from strong to weak, going left to right. The leftmost is near perfect, so a straight line, all the points lying on a single straight line, that would be a perfect correlation. So what we have on that left graph, it's not perfect, but it's near perfect. It's a very, very strong correlation. The middle one is relatively strong, so there's very small variation from the line. Mostly those points are hugging the line very close to it. Whereas when we get to the one on the right, that's a much weaker correlation. Yes, there's a general pattern, but there's a lot of variability now. And the more variability there is, the harder it is to discern a particular pattern. Here are some negative correlations. Same thing. Near perfect on the left, very strong in the middle, hugging the straight line, and then much more variability on the right, a much weaker correlation on the right. Truly uncorrelated data shows no upward or downward trend at all. Imagine just taking a handful of pennies, throwing them in the air, and letting them land on the floor. Just a totally random array. That's what we're talking about when we talk about uncorrelated data. The graph that's given on the test will not test the subtle boundaries between weak correlations and no correlations. Either the graph will have a very clear correlation or it will have none. Sometimes to demonstrate the trend of a correlation, a graph will include something called a regression line, also known as a trend line or a best fit line, and this shows the general trend in kind of abstracted into a single line. So you can see sort of the core pattern. A regression line is a model used to make predictions about the relationship of the 2 variables. So for example, if we picked this value of x and we wanted to predict what would we expect for the value of y, we'd expect something that was on the line. Now, with random fluctuations, it might be slightly higher, slightly lower than the line, but on average, we'd expect it to lie on the line. Points above the line have a y variable higher than predicted. Points below the line have a y variable lower than predicted. So here's a practice question. Pause the video and then we'll talk about this. Okay, the trend line indicates for a given body mass index what the expected basal metabolic rate would be for the individual. So given say a body mass index of 30, we'd expect a basal metabolic rate right there, a little above 1600. In this group, how many individuals have a basal metabolic rate higher than predicted? So really, this is just asking us to count the points above the line. Now, this is a funny thing about data interpretation questions. Often when you actually interpret what a graphical question is asking you to do, it's something so simple that a grade school student could do. When we phrase it like that, count the points above the line, a 3rd grader could answer this question now. 1, 2, 3, 4, 5, 6, 7. That's how many points are above the line, 7. So I point this out merely to point out, don't be afraid of the easy answer. Graphs are supposed to make things easy. And so once you interpret what a graph is asking, it may be something incredibly easy that you actually have to do to get the answer. The whole trick is interpreting it so that you figure out what it is that you have to do. But don't be afraid of the easy answer. Graphs are supposed to make things easy. In summary, scatterplots visually display the relationships of 2 variables over a group of individuals. The exact location of the dot indicates the value of the 2 different variables for that individual. Correlations, positive or negative, are patterns that pertain to a trend of the set as a whole. They're pertaining to the whole set, the whole population, not a point-by-point comparison. And regression lines or trend lines demonstrate the overall correlation pattern. They are predictive in nature, providing a model whereby a y variable could be estimated from a new x variable.